So what's up mga kache? It's Kuya Daily here. So I'm back with another checkout lesson. And thank you for supporting me and thank you for viewing my other video, which is the density and specific gravity. So if you haven't watched it yet, so I'll post a link here in the upper right hand corner of the screen and make sure to watch it. And for this lesson, I will be discussing the concentration. Okay, so we'll be discussing about concentration. Let's just define few terms. Okay, so concentration. So it designates the amount of component or solute in a mixture divided by the total of the mixture. So an example of this is maybe in mass per unit volume. So maybe in mass per unit volume. So the units may be pound mole of pound mass of solute per cubic feet of solution, or grams of solute per liter, or pound mass of solute per barrel, or kilogram of solute per cubic meter. Then we also have our moles per unit of volume. So the most notable here is the gram mole of solute per liter, which is you have the molar unit, right? So the M, it's mole per liter, so it's also a concentration. It is denoted by grams because it is derived from grams. Okay, so gram mole per liter. And then we also have our weight fraction or mass fraction, the ratio of the mass of a component to the total of the mixture, fraction or 8%. Then we also have our mole fraction, which is the ratio of the moles of component to the total moles of the mixture, fraction or 8%. So we have talked about that in the previous videos, okay? And then we also have our parts per million and then our parts per billion. So it is a method of expressing the concentration of extremely dilute solutions. And then ppm is equivalent to a mass or weight ratio for solids and liquids, and it is a mole ratio for gases. So I've talked about this. If you are given the ppm of gases, it always means it is a mole ratio and it is in mole basis. And if you are given for liquids and solids and liquids, and always it denotes mass basis. Okay, so another unit for parts per million. You can say we have your microgram per gram, or it is also equivalent to milligrams per liter. And then it is also equivalent to grams. You have grams, and then is divided by a million or 1 million grams. Okay, so that's that. So it is also equivalent to that. So we also have our parts per billion. Okay, so we have our parts per billion. So which also denotes nanograms per gram, or you have your grams per 10 to the 9 gram. Okay, so that's that. And then we also have our parts per million by volume, ppmv, and parts per billion by volume, so ppbv. So it's the ratio of the volume of the solute per volume of mixture, usually only used for gases. So in the chemical engineering, we are not really concerned by ppmv, but we are concerned with ppm and ppb, and then the previous units that I have discussed in previous slides. Okay, so we have our sample problems. It's not dilly-dally. In normal living cells, the nitrogen requirement for the cells is provided from protein metabolism, so i.e. the consumption of protein in the cells. So when cells are grown commercially, such as in the pharmaceutical industry, ammonium sulfate is usually used as the source of nitrogen. So determine the amount of ammonium sulfate consumed in a fermentation medium in which the final cell concentration is 35 grams per liter in a 500-liter volume of fermentation medium. So assume that the cells contain 98% of nitrogen and that ammonium sulfate is the only nitrogen source. So we are asked for the amount of ammonium sulfate consumed. Okay, so we are also given the volume of the fermentation medium, 500 liters, and there its concentration, 35 grams per liter. And then in the cells, we also have the 98% of the nitrogen, which will be used in our calculations later. Okay, so we have to have our basis. So we are given the volume already. So we will now use the 500 liters of broth as our basis. Okay, so basis is the 500 liter broth. Okay, so in the industry, we call that broth. It contains all the nutrients needed for the fermentation to happen. Okay, so 500-liter broth, and then we have our concentration. So let's solve for the amount of ammonium sulfate needed for our cells to grow. So we have our 500 liters of our broth, and then we'll get the grams of the cells there. Okay, so the 35 grams per liter is the cell concentration. Okay, so 35 grams of cells per liter. Then uh, in every in every cell, it is it has the 9% weight in the cell. Okay, so it's 0.9 uh, grams of nitrogen per gram of cell. Okay, and then we will get the moles of our nitrogen. So it's just divide that by the molar mass, and then we will now get the amount of ammonium sulfate in that was consumed. Okay, so 1 mole of ammonium sulfate is it has 2 moles of nitrogen. Okay, so on N, as you can see here, there are two N's, the two nitrogens in our ammonium sulfate. And then let's just multiply to get the mass of the ammonium sulfate that was used in the fermentation. We just have to multiply it by its molar mass. Okay, so the molar mass of ammonium sulfate is 132 grams. Ammonium sulfate. And okay, so get your calculator and solve this. So final answer is 7,425 grams of ammonium sulfate. Okay, so that's the final answer. Okay, so let's move to the next problem. So the current OSHA 8-hour limit for hydrogen cyanide in air is 10 ppm. So a lethal dose of hydrogen cyanide in the air is, so from Merck Index, 300 milligrams per kilogram of air at room temperature. So how many milligrams of HCN per kilogram of air is 10 ppm? So what fraction of the lethal dose is 10 ppm? So we are asked for the mg per kg. So it's actually mg HCN per kilogram of air, and the fraction of the lethal dose. Okay, so fraction of lethal dose, meaning we will be dividing it by 300 milligrams per kilogram later. So now we will convert the ppm to milligrams per kilogram for us to answer this question. Okay, so we'll start by 10 ppm. So basis, we are given the 10 ppm. So 10 ppm, is this a mole basis or a mass basis? So if you answered mass basis, and then so you're not right. So this is actually in mole basis. Okay, so 10 ppm. So I have showed you earlier the equivalence of ppm, right? So we will choose one of them. So it has milligrams per kilogram or micrograms per gram. So we will use the easiest one, which is the grams per 1 million grams. But this is in mole basis, right? So it will be in mole. So gram mole of HCN over gram mole of air plus HCN. So because it's in solution, right? But if you compare the amount of HCN over the amount of air, so it becomes insignificant. Okay, so will now only become G mole HCN per gram mole of air. So that's that. Then we will just multiply this here. So 10 times this factor here. So we will have our 10 gram mole of HCN over 10 to the 6th gram mole of air. Okay, so that's for us to have an easier solution later. Okay, so let's just convert all of the factors there. So let's convert all of the values to milligrams over kilogram. Okay, so 10 gram mole of HCN over 10 to the 6 gram mole of air. So let's convert. So let's convert the HCN first. So we will get the molar mass for us to get the milligrams. So the molar mass of HCN is 27.03 grams of HCN per gram mole of HCN. And then we will convert it directly immediately from grams to milligram. So we have 1000 milligram of HCN is equal to 1 gram of HCN. Then so that's settled now, and then we will convert now the air to kilograms. So the gram mole of air to kilograms. So we have the 1 mole of air is 28.96 grams of air. Okay, and then we will convert that to kilogram. So 1000 grams of air is equal to 1 kilogram of air. So you will use your calculator to solve for this. So we now have our 9.33 milligrams of HCN per kilogram of air. So we have answered the first question. Now the second question. So we'll just divide 9.33 by 300 for us to get the fraction. Okay, so we just put it here. So 9.33 over 300 is equal to 0.0311. So far it's far from the lethal dose. Okay, so we're still safe. Okay, so next problem. So we have the specific gravity of a solution of the potassium hydroxide at 50 degrees Celsius is 1.0824 and contains 0.813 pounds of potassium hydroxide per gallon of solution. So what are the mass fractions of KOH and H2O in the solution? Okay, so if you are given here, so it's what will we use as basis, right? So we are given this is in solution. This is in solution, right? So we will have to think of it as in mass basis. Okay, so or we could also use the volume basis, right? So we have the per gal of solution. So why not use it so that our calculations will be easier. So we will use 1 gallon of solution. Okay, that's what we will be using. So we are asked for the mass fractions of the KOH and H2O in our solution. So to get the mass of our solution, just have to make use of our specific gravity, right? So this is specific gravity, and then we are given in pounds per gallon. So what factor or what number will we multiply to 1.0824 to get the pounds in the numerator? The last video, you can remember, it is 62.4. Okay, so 1.0824 62 times 62.4, and then we'll have the 67.54 pounds of solution per cubic feet solution. So we'll just have to convert that to cubic feet. Okay, the cubic feet, we'll just have to convert that to gallon. So in 1 cubic feet, 1 cubic foot, you have 7.481 gallons. So if you will search this in your Paris, so you can find this in table 1-4, I think. And then we will multiply that by our basis so that the units will cancel, and then we will be left with pounds. Okay, so multiplying that, we will have the mass of solution be 9.03 pounds of solution. So that's we are going, or that's what we are trying to get here, the mass of solution, because we are asked for the mass fractions. Okay, so now let's get the mass fractions of every component. So mass fraction of fraction KOH, and then mass fraction H2O. So we have 0.813, right? 0.813 pounds. So we multiplied it by the basis now, so that our calculations will be easier. So 0.813 pound of the solution is the potassium hydroxide, and then divided by the total weight, total mass of our solution. So now we will have 0.09. And then to get the mass fraction of water, just uh, subtract it from 1. And then you will get the mass fraction of H2O as 0.91. Okay, so these are the answers. Okay, so the last problem I'm going to give you. So 27 pounds of chlorine gas is used for treating 750 gallons of water each day. So the chlorine used up by the microorganisms in the water is measured to be 2.6 milligrams per liter. So what is the residual excess? So residual or excess chlorine concentration in the treated water. So the problem here is that in the I've discussed to you the water treatment plant. So the chlorine gas is used for disinfection of our drinking water. Okay, so 27 pounds of the chlorine is used. Okay, so we will be calculating for the residual chlorine. So from the from the uh, chlorine that was added, we will get a concentration of that, and then we will subtract it by 2.6, and then we will get our residual chlorine. So this is actually easy. So just have to calculate for the total, the chlorine that was added. So Cl added. So we have 27 pounds over 750 gallons of water. So we will just convert that until we get the desired concentration of milligrams per liter. Okay, so 454 grams is in 1 pound. Okay, so you've learned this in the mole video that I have shared. And then to converting grams to milligrams, so that, and then we have the 1 gallon over 1 gallon is equal to 3.785 liters. Okay, so if you get the answer using your calculator, you will have 4.32 milligrams per liter. Okay, so and then we will get our residual, just subtract 2.6 from 4.32. Okay, so residual Cl, residual chlorine, so 4.32 2.6 is equal to 1.72 milligrams per liter. Okay, so it's that easy. That's the answer for that problem. Okay, so that's the end of the sample problem. So I'm gonna give you practice problems now. So it's really easy. So I hope that you will answer it in the comments below. And then as a bonus, I'm going to give you the boss problem. Okay, so this is a boss problem, and if you can answer it, then you will be really blessed that you answered it, because it is one of the first activities that your teacher will give you. Okay, so if you can answer this, consider yourself blessed. Okay, so that's the end. That's the end of our short video. So I hope that you have learned much, and then if you have any questions, you know where to find me. Okay, so I will I am still giving the link to my Facebook profile in the descriptions down below, and then the reference book that I'm using, I'm listing it here. So okay, so it's Sino and release. Okay, so that's it. Thank you for watching. Bye bye.